Hi again, guys. So today we're going to talk about two topics dealing with gases for AP Chem here. So we're going to talk today about effusion and diffusion. And I want to start off by defining what these terms mean. They're both processes that occur with gases, but they're slightly different from each other. So I'm going to start with diffusion. Diffusion, a basic definition of diffusion is it is the random mixing of gaseous particles. Okay, the random mixing of gaseous particles. So one example of diffusion that we're happy about is that the CO2 that we exhale, or let's say that a power plant is generating CO2 by burning natural gas or coal to make electricity, that CO2, when it comes out of the power plant, if it didn't diffuse, you'd have this big blob of CO2 sitting right by the power plant, and you couldn't live there. We wouldn't be able to go anywhere close to the plant. People in the plant would die because the CO2 did not mix into the atmosphere and get diluted. So we need diffusion in many cases like this, okay? So that is just simply the random mixing of gases. Now, would that random mixing be supported by the KMT? The rules of the KMT, would that support this idea that if I have two gases that are in a space, that they will eventually completely mix and be evenly distributed? Well, if you look at the rules of the KMT, one of them is that gases are in constant motion, that the particles of gases, unless it's super, super cold, approaching absolute zero, that those gas particles are moving all the time. So the fact that they would mix makes total sense. So an example of this mixing would be a lady comes into a room and she's got perfume on. And within a few minutes, everyone in the room really can smell the perfume if it's strong enough, she has enough on. So that would really make sense. If she walked into the room, then basically her perfume, the only way you're going to be able to smell it is if that perfume gets into the air as a gas. So those particles, and I don't know if, I hope you guys can see them, they're a little bit different color than the other air particles. So the air particles are blue, if you could see it. And the perfume particles are red. Now, right in the very beginning, when she first walks into the room, those red perfume molecules are going to evaporate off of her and go into the air. But they're moving. They're constantly moving, and so are all these other particles. So over time, what will happen is these particles are going to move off in different directions, bouncing off of the air molecules, and eventually they're going to start to spread out. You're going to see them moving further and further away from the lady with the perfume until finally they're going to go across the entire space that's occupied. Some of that perfume is going to be in that whole space, but it is important to note that that perfume will be diluted. You only have so many molecules out there, and as they mix, as you get this random mixing, they're also going to spread out. And so they may be a little bit harder to detect if you're trying to smell the perfume. And one other kind of interesting thing with perfume, if you watch ladies put perfume on, where do they usually put it? They'll put it on their wrists, sometimes on their neck, that kind of thing. The reason why, and people may not realize that they're doing this, those are areas where blood vessels are close to the surface, so they're warm. They're warm parts on your body. Think about what the KMT would say. If I put perfume on a warm part of my body, like my wrist or my neck or something like that, then that warmth is going to cause more of that perfume to evaporate into the air. And those molecules are going to be a little bit warmer than their surroundings, so they move faster. So putting the perfume on those areas make it so that the odor of the perfume goes out into the air quicker. Okay? So that's a basic idea of diffusion. Effusion, a basic definition, it is the passage of a gas through a tiny opening and then into an evacuated chamber. That's a really strict definition. And so we don't really see a whole lot of effusion because of the fact that here on Earth's surface, we don't have many cases where we have a gas that's exposed to an evacuated chamber, like a vacuum chamber. Not something we normally see. Okay, that's not real common. If you were in space on the International Space Station and somebody messed up and punched a hole in the side, then the air that's inside the space station would effuse into space. All right, it's going to leave that space and go into the evacuated chamber that is outer space. It's a vacuum. Okay, something that would come fairly close to it is like if you were to punch a hole in a tire, like you run over a nail or something, similar thing. Or the example I like to use is a latex balloon. Maybe this happened to you when you were a kid. You went to the cattle call parade or something like that, and this guy's walking along with a bunch of balloons, like 50 balloons, helium balloons. And you beg, Mom, can I have a balloon? Can I have a balloon? And so in order to get you to be quiet, she buys, to make you happy, she buys you a balloon. Now, when you're 6 years old or something, she's not just going to let you hold the balloon because you're probably going to let it go and away it'll go if it's a helium balloon. So she ties it around your wrist and you walk around with your balloon all day. You go home finally and your mom says, you've had a big day today. It's time to go take a bath and go to bed. So you take the balloon off your hand, off your wrist, and tie it to a chair in your dining room or something. And off you go to get ready for bed. You go to sleep thinking, I'm going to get up tomorrow and play with this magical helium balloon. And you get up the next morning, and what do you see but your helium balloon dead on the floor? Major disappointment. You are the victim of something that's pretty close to effusion. Let me explain. If you look at a latex balloon, a regular rubber balloon, and if we put helium in it, okay, remember that these helium molecules that are inside of here, or actually they'd be atoms, they're moving all the time. They're bouncing off the inside of the balloon. They're moving through the balloon. They're moving all over the place. Okay? The thing about latex, though, is that rubber that balloon's made out of, it's not a solid sheet, even though it looks that way. If you can look at it microscopically, there are tiny little openings, little pores, really, that are in that latex, if you look at it microscopically. So little dinky openings, okay? Now, because of the rules of the KMT, this helium that's in here is constantly bouncing off of the inside of this balloon. And every time that it hits the balloon, it's an opportunity. It's an opportunity for that helium, if it hits it just the right spot, it can slip through one of those pores and escape. That is essentially the process of effusion, short of the fact that we don't have a vacuum out here. Okay? So why did your balloon die overnight? Because the helium escaped through these tiny pores. Now, if I had a balloon that was filled up with air, if we got another balloon here and we filled up this balloon with air, so this is primarily going to be nitrogen and oxygen. Those are the two main constituents in air. This balloon's the same. It basically is going to have those same pores that these could escape through. So why doesn't a balloon that you've blown up with air, why doesn't this one shrivel and get much smaller like the helium one did? Well, this comes down to the size of the molecules and how fast they're moving. If these are both at the same temperature, they're not going to be moving at the same speed because this has a mass, one helium has a mass of 4 grams per mole. Okay? 4 grams per mole. Nitrogen's 28 grams per mole, and oxygen's 32 grams per mole. And so the fact that both of these are much heavier than this means these guys move slower than these guys do if they're at the same temperature. We went over that yesterday. All right, the fact that the lighter they are, the faster they have to move in order to have the same energy that these guys would. Now, why would they have the same energy? Because they're inside your house and they're at the same temperature. Remember, same temperature, if two gases are at the same temperature, they have the same kinetic energy. That doesn't mean they have the same velocity. The one that is lighter is moving faster. If it's moving faster, that means more opportunities to hit the inside of this balloon and possibly escape. These guys don't have nearly the number of opportunities to escape because they're moving slower. They don't hit the inside of the balloon as often. What's more, think of it this way. The air that's outside of this balloon is also made of N2 and O2. And so those molecules are going to be colliding with the outside of the balloon, and that gives them an opportunity to go the other way and go back into the balloon. So essentially, for every one you lose, you're going to replace it with a new one. If you're talking about these two, there's very little to none to no helium that's out here. So there's nothing to replace what escapes. Okay, so kind of actually it's a couple of things. Number one, you can't replace them. The heliums, I mean, you can replace these. Number two, these guys are physically much smaller than these guys are, which means when they hit that inside of the balloon, they're more likely to be able to go through one of these tiny openings here than these guys are. These are big molecules, and they have a hard time getting through that small opening. Okay, they got to hit it just right. And there is the other thing is these guys are moving faster. Though their lower mass means faster motion. Faster motion means more opportunities to hit the side of the balloon and maybe hit where one of those pores are. So that latex balloon is a great example of effusion, but also it's a good thing to help us illustrate some of the rules of the KMT. So when we looked at the balloon here, what we saw is that process that approximates effusion, that process where the balloon loses its helium. A part of that rate at which the effusion will happen is dependent upon, a big part of it, is dependent upon how fast that the helium atoms are moving. The faster they move, the faster that helium's going to effuse. So the fact that it's a very light atom, that it doesn't have much mass, means helium's going to effuse pretty quickly, faster than air would. If I heated up that balloon, what I would find is that that rate at which the effusion happens would also go up. Again, because heating it up makes the particles move faster. It's all about velocity. But the way we generally measure effusion is by comparing the rates of effusion. So this gas effuses twice as fast as that one. This gas effuses half as fast as the other. All right, we compare the rates of two gases. And the reason we have to do a comparison is there's a lot of other factors that are involved. So all things being equal, if both gases are inside of a latex balloon that have the same properties, the same pore sizes, the same pressure, all that stuff is the same, we're only going to compare the rate at which the effusion occurs. We have to do this comparison because of the fact that there's just too many other variables to consider. Okay? So when you think about getting an equation to measure effusion, then if the velocity of the particles is a big factor for effusion rates, then we need to have a way of comparing what those velocities are. And the way we do this is we already know that if two gases are at the same temperature, we already know they have the same kinetic energy. Remember, the KMT says that your temperature is dependent upon your average kinetic energy. So if I have two gases and they're at the same temperature, they must have the same kinetic energy. But because their masses may be different, they won't have the same velocity. And so if we really want to know how fast particles are moving, this is all about the mass of the particles. The heavier they are, the slower they move. The slower they move, the slower your effusion rate's going to be because they don't get as many opportunities. Okay? This also goes for diffusion. So as we talked about with the perfume in the previous scene here, if you put perfume on an area of your body that's warm, it will be warm and it will diffuse quickly. Okay, so diffusion also, it's going to have something to do with temperature, but if I have a perfume molecule, a particular fragrance, they're just chemicals, that's all they are, you guys. If there's a particular fragrance that doesn't have much mass, it will diffuse quicker. It'll move through the room faster. Okay? So we've come up with, I think it was a Scottish dude, it said in the book. His last name, big surprise, was Graham. He comes with Graham's law of effusion. And the one thing that you guys should notice, number one, you're comparing two rates. The rate of effusion of gas A over the rate of effusion of gas B. And notice that on the other side, that these two are inverted. So these are inverted. This is the molar mass of B over the square root of the molar mass of B over the square root of the molar mass of A. And so your A and your B switch places, switch sides on top of that fraction. Is the one thing you should notice about Graham's law. Now, if you encounter a problem, you guys, that deals with effusion, if they mention effusion, you almost certainly are using Graham's law to solve that problem. I do not know of another formula that deals with effusion other than Graham's law. So if you get a question on your AP exam and it starts talking about rates of effusion, you know you're using this. Okay? It is the only formula for that. So this is the formula that you will utilize when you deal with any questions that deal with effusion and many questions that deal with diffusion. Because when you think about it, the time it takes a particular gas to move through outer space is also partly dependent, mostly dependent, on the mass of that gas. Again, light gas particles are going to diffuse quickly. Heavier gas particles are going to diffuse more slowly. Okay, so we're going to go over an example of that to get you guys prepared for some questions on them. So an example using Graham's law. We're going to do kind of a real world example here. So let's, we're going to look at a particular substance that contains uranium. Specifically, uranium hexafluoride, UF6. Now, the thing about uranium is that uranium has two different isotopes, one of which is much more radioactive than the other. And by radioactive, what I mean is it has a short half-life. It breaks apart in nuclear decay fairly quickly. And that particular isotope is uranium-235, okay? It has 235 protons and neutrons combined, and that's not particularly stable. And so it will break apart and release tons and tons and tons of energy. Another isotope of uranium that's pretty common is uranium-238. 238 has more neutrons. That's the reason why that number is 3 bigger than that one. It has 3 extra neutrons. This one's not quite as radioactive. Now, if you want to make fuel for a nuclear reactor, or heaven forbid, for a nuclear bomb, you need to isolate this stuff. You need to separate the 235 from the 238. And one way that you can do that is diffusion. So what you would do is you turn them into a gas, and by reacting them with the fluorine, that is a gas. And then you release both of these compounds with the different isotopes at the same location, and you allow them to start to diffuse. Now, the idea here is this one has a lower mass than this one does, which means what about its speed of diffusion? The lighter they are, the faster they move. Okay, if they're both at the same temperature, this guy right here is moving faster than this one. Okay, so if I want to isolate this particular compound from this particular compound, I can use the rate at which they diffuse to help me figure that out. So if I release them again at the same time, what I would find is that after some period of time, that these UF6, the ones that were heavier, that had the uranium-238 in it, they may have diffused to, say, that location. But these ones, because they're lighter and move a little bit faster, they may have diffused a little bit further. They got a little bit further. So if they were both released from here, when you get to this point, the 235 is going to be a little bit ahead of the 238. And the longer that I make them go, because this one continues to move faster, the further that I let them go, the bigger the separation is going to be. Now, does that mean that every 238 is going to be back here where the blue is? No, remember, their speeds are a little bit random. That's just average speeds. So they're going to get further apart, but there will still be a few, if I represent these as separate particles, there'll be a few that are further back. There will be a few that are further forward. But the average, what most of those uranium, these ones, the heavier ones, they're going to be about right here. The pink ones, most of them are going to be up here. These are the 235s. They're lighter, they move faster. But there will be a few that are still back here and a few that are further forward. So what they do to separate these two is they'll get to some point and then they close off the chamber. They'll close off that chamber, and that will trap more of the heavier ones. There's going to be a higher percentage of heavy ones back here of 238s, and a higher percentage, well, relatively speaking, more of the 235s will get trapped up here. Now notice, there's still some 238s there. So how do I get rid of those? I do this over and over and over and over again. This is how, when they first built the first nuclear bomb, and they needed 238. This is how they separated the two to get that nuclear fuel. We're worried about other countries in the world getting nuclear bombs. They could do this process. Another way they do this is by taking that material and spinning it really fast in what's called a centrifuge. And so those are ways that you can separate these things that have different masses. So my question would be then, what's going to be the ratio of effusion rates? How much faster will that uranium hexafluoride that has the uranium-235 in it, how much faster will that one effuse than this heavier one that has uranium-238? This is something that we can answer using Graham's law. And the way that we usually do this is when I do the ratio, I want to put the heavier isotope or the heavier molecule on the bottom of the ratio. So I'm going to say the effusion rate of the heavier of the two. Well, if I look at these two, the heavier of the two is this one. Okay, so I'm going to take the effusion rate of the uranium hexafluoride that has the 238 in it, and that'll be on the bottom. And on the top, because I'm going to compare these by making a ratio, a fraction, I'm going to put the lighter one. So this will be the effusion rate of the 235 uranium hexafluoride. Okay. Now, if this was another problem that had two different substances, let's say that you were comparing the effusion rate of ammonia, NH3, and oxygen, O2. Well, this one has a mass of 32, and this one would be 14 plus 3 is 17. So in that case, if I was comparing these two. I just don't want you guys to get confused in that it's the same compound, just with different isotopes in it. So let's say you were comparing these two. I'm going to put the lighter one, when I write this ratio, I'm always going to put the lighter one on the top and the heavier one on the bottom. This one that's 32 is going to go on the bottom, so I'd say effusion rate O2. And here I'd say effusion rate NH3. Okay? Lighter one on top. Just think the lighter one floats to the top. Think of it that way. Okay? So now, if you remember what I wrote in Graham's law, when I wrote it down in the last scene, this is going to be equal to the square root of the molar mass, and these guys flip places when you go over here. So this is going to be the molar mass of uranium hexafluoride, where the uranium was uranium-238. Okay? Remember, that M has nothing to do with this equation. It just means molar mass. That's it. Over the square root of the molar mass of the uranium-235 hexafluoride. Okay? So that's what our statement for Graham's law is going to look like. And again, you're going to get some examples that you don't have to worry about this mass number. It's really just the formula that's in there. Now, if I work out those numbers, and I did them already, if you add up the molar mass of the uranium, which we're essentially giving you the uranium numbers here, and then fluorine is 19, is its molar mass from the periodic table. So 19 times 6 is 114. So if I add 114 and 238, what I'm going to get is the square root of 352. On the bottom, again, 6 fluorines is 114, 19 times 6. 114 plus 235 gives me 349. Okay? So if I work that out with the calculator, what I'm going to get is 1.0042 to 1. Okay? So what does this mean? This would basically mean that in the time it takes the 238 to go 1 meter, the 235 is going to go 1.0042 meters. It's not a big difference, but it is a difference. So for instance, if I wanted to cut this off, what I would say is that when the 238 has gone 100 meters through this tube, that the 235 would have traveled 100 meters plus 0.42 additional centimeters, like half a centimeter further. So where that barrier goes, that's going to be the way that I'm going to separate these two. But again, I can see that the 235 is going to effuse a little faster than the 238 is because of the fact that it was lighter. Okay? You'd get bigger differences, bigger fractions if you use numbers like this. And those are the ones you're going to see in your homework set. Okay? So you should see bigger differences on those. You guys can, of course, send me an email or send me a message if you want to double check yourself when you do your first one on that homework. Just make sure you got the right answer. Okay? So this is effusion and diffusion, one of the properties of gases. And that's pretty much it for what we're going over today. We'll talk to you later.